So a little bit more from section 7.1. We're going to go over sample size calculations. And the sample size is to control your margin of error. And we just looked at some data from Dr. Atisha's study on blood lead levels from Flint. And we found a 95% and 99% confidence interval. Now these confidence intervals really reflect an error, a distance from our p hat. And that distance is going to be e. So what this is it's p hat minus e to p hat plus e. Now if you wanted this confidence interval to be narrower, then you'd have to make e narrower. And the only way to do that is to try and figure out a larger sample size. How big do we have to make this to, say, keep this between 1 and 2% or 3 and 4%, whatever values you want to choose. And fortunately for us, there's a nice way we can do that. There's a formula we can plug into to solve for our sample size calculations. That's on page 307. There's two formulas here. It depends on what you know, if you know something. If you have an estimate of p hat, there's a proportion of your populations that satisfy some criteria. If you have that estimate, then we can use this formula to try and find the proportion or the number of samples that we need to draw to control our error. If you don't know what p hat is, then we're going to replace this p hat q hat by 0.25. So this is actually an easier calculation than this one. The one thing you have to be careful of is knowing what z sub alpha over 2 is. The rest of these things I think we understand. But z sub alpha over 2 is the z-score that puts alpha over 2 of the area in the right tail of a standard normal curve. So let me draw that for you so that you have a nice visual. So here's our normal curve. The standard normal curve has what here for the center? What value? The mean, and in this case 0. So z sub alpha over 2 is going to be the point on the curve that puts alpha over 2 of the area in the right tail. So z sub alpha over 2. And let's remind ourselves how we can find that. Now I'm going to do it two ways. There's actually three ways, but I'm not going to go back and do Google Sheets right now. Let's look at the graphing calculator. We'll also look at StatDisk. So with the graphing calculator, if, for instance, I wanted to find the value z sub 0.01, then on the graphing calculator, you're going to go to distributions. So you hit second and then vars. That gets you to the distribution. What we want from here is the inverse normal. Now I've been told that a lot of your calculators don't give you this option for the tail here. So if that's the case, you're going to have a default option, and that default option is going to be the area in the left. Well, if I'm trying to find z sub 0.01, then that puts 1% of the area in the right tail. How much of the area is in the left tail? 1 minus that, so 0.99. So let's do 0.99 of the area. The mean is 0. Standard deviation is 1. That's for a z-curve. Area in the left tail. And bam. This is what our command looks like. Nice. So 2.326, etc. That's going to be our value for z sub 0.99 or z sub 0.01. If you have an older calculator, if you're inverse norm is not menu driven like this is, then the form of the command is inverse norm and then area to the left, comma mu, comma sigma. That's the form that you would type it in. And the comma is right above the 7, so you can directly access that. So you should get about 2.326 would be that value. This is something I'd want you to be able to find on an exam, say z sub alpha over 2 for a particular value. Now it's going to be part of our calculation in these sample size questions. We'll start with problem number 34B, and we'll backtrack and do problem 34A, which is actually going to get a little easier than 34B. A sociologist plans to conduct a survey to estimate the percentage of adults who believe in astrology. How many people must be surveyed if we want a confidence level of 99% and a margin of error of 4 percentage points? The margin of error is important along with our confidence level. So problem 34, we've got a 99% confidence level. And that's going to tell us something about alpha. And we want an error of 4%. What's 4% as a decimal? 0.04. Thank you. Now our confidence level is 1 minus alpha. So if I wanted to figure out what alpha is, then I could solve here. 0.99 equals 1 minus alpha, or alpha is 1 minus 0.99, which gives me, of course, 0.01. Nothing dramatic there. But from here, I need to find z sub alpha over 2, which is z sub 0.01 divided by 2, or z sub 0.005. Now, it's not 5%, it's 0.5%. So let's keep that in mind when we look things up. This time we're going to do stat disk. And I'll draw this for us here. I want the point on the standard normal curve with 0.005 of the area in the right tail. So with stat disk, let's go to analysis, then probability distributions. And the first one in there looks pretty good. The normal distribution. Now, it depends on what you've got. You can either type in the z value and get the area, or type in the area and get the z value. Now, in this case, we want the area. It's asking for the area in the left tail. What you have to realize is that area in the left tail is 1 minus the area in the right tail. So 1 minus 0.005 is 0.995, and that's going to be the area in the left tail. You click Evaluate, you should be able to get something like this. If you're using a graphing calculator, again, you should still get something like this, 2.575, call it 2.576. If we round it off to the nearest thousand, yes. Is everyone able to get this? 2.5, was it 586? 576? 576. Okay, thank you. Everyone's able to get that number one way or another using your favorite technology. Yes? Okay. Let's put this in now together with some more information and find the sample size. Now that calculation is going to be n equals z sub alpha over 2 squared times p hat times q hat divided by e squared. So in part B, it says, use information from our previous Harris survey in which 26% of respondents said they believe in astrology. So what's that 26% representing for us? Does anyone know? Yeah, that's p hat. All right, so let's fill things in here. It's going to be 2.576 squared times p hat, which is 0.26. Now, someone else for q hat. What's q hat going to be? If p hat is 0.26, what's q hat going to be? 1 minus that. So 1 minus 0.26, 0.74. Thank you. 0.74. Now, we want to find this to within a margin of error of 4%, which means in the denominator, I'm going to put in 0.04 and then square it. Let's take out some calculators here. So 2.576. Oops. And then I'll hit the square key on the left-hand side. Times 0.26 times 0.74 divided by 0.04. And again, hit the square key. You should get something like this, 797.97. You're able to get that off your calculator. Does anyone need to borrow a calculator? I got just one or two here. All right. Maybe that's an underestimate. Okay. There we go. Yeah, thank you. Someone's paying attention. All right. So we get 797.95. Can I take 0.95 of a sample of a person or no? So what should I do with this? Round it. Now, if this is 0.95 or 0.05 or 0.25, whatever it is, you always round up in these kinds of calculations. I know that a lot of people are used to that 0.5 rule, but in these calculations, you always round up. So if you get a decimal at all, go to the next whole number. How are we looking on part B? So what this is doing is it's going to control the size of my confidence interval. So that if I want to know the percentage of people who think America's heading in the right direction, and I want to know that to within 4%, then I can do a sample size calculation like this. So it might be 51% of us, think America's heading in the right direction, plus or minus 4%. That's that margin of error you see accompany a well-done poll. So sometimes you want that to be even smaller. You might like, no, I need to know within 2%. Okay, you look at what happened in the last election. All right, there was a lot of margin for error, and people were predicting Hillary Clinton would win, but guess what? Donald Trump won. And part of the problem is that there is a little margin for error. I mean, there's other things going on as well, but if you have a much larger sample size, you can start to control the width of your interval and narrow down the margin for error. Okay, let's take a look at part B here. Or excuse me, part A. Part A says, let's assume we don't know anything. We don't have a previous study. Well, if you don't know anything, then you got to kind of assume a worst case of this formula. And the worst case of this formula is if p hat is 0.5, and if p hat is 0.5, what is q hat? 0.5. 0.5 and 0.5, right? 1 minus 0.5 is 0.5. Let me help you out here. P hat is 1 minus Q hat, or Q hat is 1 minus P hat. So if P hat is 0.5, then so is Q hat. So if you make P hat and Q hat both 0.5, then this becomes 0.25. 0.5 times 0.5 is 0.25. So that's the formula we're going to work with. And that's assuming that we don't know what's going on with any previous studies. So n equals z sub alpha over 2 times 0.25 divided by e squared. So it's actually easier to use than our previous formula because we don't have to worry about P hat and Q hat. It's just a 0.25. That should be squared. So 2.576 squared times 0.25 divided by 0.04 squared. So this is just really kind of the worst case scenario. See if you can't figure that out. What are you getting for this? Now we're using the same z sub alpha over 2 that we had for the last problem. We're still assuming we're trying to find this number with 99% confidence. What are you getting this time? What's the raw number? So you get 1036.84, but then it rounds up to 1037. Please make sure you round your answers up in these types of calculations. It's the only time I'm going to ask you to round up like this. Maybe I shouldn't say only time, but it's the only time that I can think of at the moment, off the top of my head. Are you comfortable with these calculations? All right, everyone's pretty good on these? Yes, good? Yay. Yay, well done. Thank you. Thank you. All right. For homework, this is section 7.1. Now, I've assigned a lot of this, so there's only a few problems that I want you to tackle. They're on sample size calculations, problems 31 through 35.